Trigonometric. Okay. So, ladies and gentlemen, so the main important thing I want to get started with you is when we're looking at our trigonometric ratios, or even beginning with trigonometric ratios. But the main important thing, guys, we have a triangle, we have a right triangle, right? And what we kind of worked on in our warm-up was that when we see a right triangle, we know immediately that we have a relationship of the sides with a squared plus b squared equals c squared, right? And we worked on that. What? Oh, OK. Nice. So we have a squared plus b squared equals c squared, all right? And that's our Pythagorean relationship that we know to find the missing sides of the triangle. Now, that's an obviously important thing that's going to come up again and again. But the next thing I want to talk about is a little bit more of like, what are the information that we look at? So we know that the hypotenuse is always the longest side, right? When we have a right triangle, the hypotenuse is always the longest side. No other side, which we call the other two, which we call the legs, are never going to be longer than that hypotenuse. But it kind of brings up a little interesting kind of question. It's like, how close is the legs, or one of the legs, compared to the hypotenuse? Like, is this half its length? Or let's pretend, like, let's look at this. Let's do a little bit even closer. Like here, what is the comparison? How big is b to c? It's like pretty close to the same size, right? Or we could look at a right triangle like this. And we could say b is not really close to the length of c, to the hypotenuse, correct? So we have a comparison, right? And basically what we're doing is we're comparing the length of one of the legs compared to the hypotenuse. But it's really important. As we keep on getting closer and closer, like this angle here, we could say keeps on getting larger and larger. B is going to keep on getting closer and closer to the size of the hypotenuse. Wouldn't you guys agree? Right? Now, it can never equal the size of the hypotenuse, though. Because if it equaled the hypotenuse, then we wouldn't have an angle anymore, right? I mean, if it was exactly the same length, then we would have like a collapsed triangle. And therefore, we would have no other triangle. And the comparison would be 1 to 1, and it just wouldn't happen. In the same respect, it might be easier to think about b could never be 0. If b had a length of 0, then we just have a line on top of like a line, right? We wouldn't even have a triangle anymore, correct? So we have this issue here, actually, that our b has to be between 0, or at least the comparison has to be between 0 and 1. The comparison of how is b to c, right? Because if it was exactly the same length, it would be a 1-to-1 relationship. But we know that can't be the case, and it can't be 0. So the ratio, or the relationship, the comparing from the side length b to the hypotenuse is between 0 and 1. So onto that kind of thinking, what we're going to do is we're going to compare how one side compares to another side. All right? And the most basic representation we have of this is our trigonometric ratios. And that's all the trigonometric ratios are. Just like in here, we could say, boys to girls, or boys, to girls, right? That's just a ratio. That is just comparing how many boys there are compared to how many girls there are, correct? So our trigonometric ratios, ladies and gentlemen, is just going to be a comparison of how long one side length is compared to another side length. And that's all it is. Now, the important thing, though, about the trigonometric ratios that you guys need to do is it's all relative to what angle we're referring to. So the first thing I'm going to give you guys is our first angle and our representation of that first angle, which we're going to use theta. Now, instead of using x and y's, which you guys use in geometry quite a bit, our most often representation of our missing angle, or just an angle of our triangle, is going to be using the Greek alphabet. So one of the more common ones we'll use is theta. All right? So the first trigonometric ratio is the sine of theta. And the sine of theta is basically comparing the length of the opposite side to the hypotenuse. Now, we know the hypotenuse. That one was kind of easy. But what do we mean by the opposite side? So here's the way that I think about it. The side that is between your angle and your right angle is what we call the adjacent side. All right? And if you think of your angle as like a projector, right? If we hung a projector on the wall and it's projecting onto this wall, you could say like this angle is projecting to this side. We call that the opposite side. So the sine of theta is the opposite over the hypotenuse. Or, in this example, is going to be b over c. And again, all sine of theta is saying is, how big is b compared to c? And that's really just what it's saying. And we know that answer is at least going to be between 0 and 1. The next trigonometric ratio is the cosine of theta. And the cosine is basically comparing the adjacent side to the hypotenuse. So we have the adjacent over the hypotenuse, which in this case is a over c. And then we have the tangent of theta, which is the comparing of the opposite side over the adjacent, which is just going to be b over a. Now, we have ways to remember them, like SOHCAHTOA, or a couple other ways to do it. But don't worry about it. It doesn't even matter, because we're going to be doing these so often. I'm not even worried about you guys having to remember them, and that's not the important thing of the class. So here is our 3 basic trigonometric functions. However, ladies and gentlemen, that is all based off the angle theta, right? Because these angles, opposite and adjacent, are based on where theta is. So what I want to introduce to you is, if I just change what angle we're referring to, and I say, let's talk about this angle up here, which I'll use the Greek semmer for alpha to represent that angle. Again, it could be x or y. It doesn't matter what, or any Greek alphabet. But 2 that I'm going to introduce from the start are going to be theta and alpha. Now, if you look at this, the side length that's between the angle and the right angle is right here. So now this is my adjacent side. And this is my opposite side. So it's all relative to the angle that you're referring to. So just don't say, oh, I got a triangle, I can find opposite and adjacent. No, you got to know what the angle is to determine what is the opposite of the adjacent. The only thing that doesn't change is the hypotenuse. Hypotenuse is always the longest, right? And it's always directly across from 90 degrees. So if I want to find the sine of alpha, it's still opposite over adjacent, or opposite over hypotenuse. However, now, since we're talking about the blue, it's not b over c, it's a over c. And that's really important for you guys to understand. To get these trigonometric ratios correct, you got to know the angle that you're talking about. So the cosine of alpha is going to be adjacent over hypotenuse. So that's going to be b over c. And then the tan of alpha is still opposite over adjacent. But now that is going to be a over b. OK, so that comes into our basic kind of realm of things. But here's where students kind of here's some issues that I have. A lot of students will write, or what I've seen written before, is the sine of, or they just say sine is equal to 3 over 5. Well, ladies and gentlemen, that makes no sense. That's like saying the square root is equal to 2. What do you mean the square root is equal to 2? No, what is the square root of 4 is equal to 2, right? The sine of an angle is equal to 3 over 5, right? So just remember, guys, these trigonometric ratios are of an angle. So just make sure when you're talking about sine or cosine, you're always inputting in the angle that you're referring to, all right? Because it's the sine of an angle. It's cosine of an angle, tangent of an angle. Right? It's not the square root equals 2, square root equals 5. No, the square root of the radicand equals whatever that value. Does that make sense a little bit? All right. So the 3 trigonometric ratios. Then we have what we call the reciprocal ratios, which I'm only going to do for theta, just because it's just redundant. So we have the cosecant of theta, which is just the reciprocal of this, which is the hypotenuse over the opposite. So that's just going to be c over b. Then we have the secant of theta, which is going to be the hypotenuse over the adjacent, which is c over a. And then we have the cotangent of theta is equal to the adjacent over opposite, which is a over b. Yep.
When we're doing this on a calculator, would you just click second?
We're going to get we'll get into that later at the end of class.
Is that the bottom?
Cotangent, yep. Now, before I move on to an actual example, Christian, when you look up here, what is something that you kind of notice What is any kind of like relationship, something that's maybe kind of interesting that's going on with what we have up there on the board? Anything. Any kind of relationships, maybe some comparisons. Something kind of interesting. No, nothing's coming to mind. Yona, do you got anything? Yeah, do you guys notice that? Look at the sine of theta is b over c. The cosine of alpha is b over c. Huh? Right? Sine of theta is b over c. The cosine of alpha is b over c. The cosine of theta is a over c. The sine of alpha is a over c. Right? Now we're going to get to that later. I just want to kind of make that point while we have this up here. But that's kind of an interesting little relationship that's going on there. And we'll talk more about that in a second. So the next thing that we're going to do is let's take a triangle and let's see if we can figure out all 6 trigonometric ratios. So no. OK. Why don't you guys go ahead and take a moment, see if you guys can figure out the missing side lengths of the triangle, and then start writing the trigonometric ratios of the problem. And then I'll come back up and we'll go through it. OK? Yes. Oh, good point. The angle, the reference is not in there, is it? That's good point. Let's talk about. There you go. Theta. But you're right. But that makes total sense, though, right? If I say find the sine, cosine, and theta, and I didn't include, or if I say sine, cosine, and tangent, and I don't give you the angle, it literally makes no sense, right? Because what is opposite adjacent? What is like we know the hypotenuse, but what is the opposite in the adjacent? So there's actually 2 things we need to take away from this. One, if we don't have the right triangle, if we don't have a right angle, we can't apply these trigonometric ratios. Okay? So you have to make sure you have that right triangle. And then 2, we got to know what angle we're talking about. So let's make theta right here. All right? And then what I want you guys to do is go ahead and figure out what is the sine of theta, cosine of theta, tangent of theta. And then we could do the cosecant, which is just the reciprocal of sine of theta, the secant of theta, and the cotangent of theta. I bet you would, because the trigonometric ratios say you have to have the hypotenuse, right? So yeah, you're right. I'm not going to give you everything you always need. Sometimes you're going to have to do a little. Sometimes you're going to have to do a little work before you can get those. Yes.
I know that's wrong.
It is.
That high. So what do you do?
Right. Oh shoot! I'm sorry. I messed this up. Sorry.
No. Because I just saw.
Good.
No.
Sorry. I have a specific idea for this. Sorry. We want this to be 3. Yes. Sorry about that. It was my bad.
Okay, so I did the other one first, so I just wanted you to check it.
Yeah, but I'm not dealing with those. Yeah, I mean, it looks good.
Yeah.
The answer is going to be very simple once you guys get to it. Sorry. Obviously, 3 squared is 9, and that was in my head, so apologize.
So the answer is 9.
No, the side length squared is 9. Yep. Well, no. A squared plus b squared equals c squared.
Square root of 36. Okay.
Give it a shot. Yep.
What are you laughing about?
Check it. Yes, square root of 36 is 6. Yep, you're good. Not that I'm aware of. All right. So let's go through it. So the main important thing, guys, this is not a Pythagorean triple, right? Right? So automatically we know that we need to apply the Pythagorean theorem. We'll just call this C. That's perfectly fine. We could say the square root of 27 squared plus 3 squared equals C squared. Square root of 27 squared is just going to be 27 plus 3 squared is 9 equals C squared. 36 equals C squared. C equals plus or minus 6. Now this is huge that I need to bring this up. Guys, we introduced the square root, right? You have to make sure you remember it's plus or minus 36. Or I'm sorry, plus or minus 6. Now, I know. Wait, no. But just hold on. To understand, though, at least I provided the plus or minus. Now, in the context of this problem, negative makes no sense. There's no orientation here, right? There's no positive, negatives, anything like that. So you are correct. We're not going to use the negative portion. But the reason why I'm bringing that up is because if you don't at least get in the habit of always including plus or minus and then deciding if it needs to be used or not, you're going to forget, because all what's going to happen is we're going to start getting into problems where orientation is used. We do have positive and negatives. So you'll have to decide, is a side length going to be positive or negative? Now, hypotenuse is always positive. So we could also go down that length. If you're finding the hypotenuse, it's always going to be positive. But sometimes these legs, we're going to need to use the negative form of them. So just recall, guys, introducing that square root, we have the plus or minus values. Again, that's one of the major mistakes I see people throughout the course having. Yes?
When would you ever have the length negative?
It's not the length is negative. It's going to be the orientation. So the length is still positive. Like, for instance, we're going to get into this later. But like, let's pretend my unit circle is this. And this was like -4. It's 4 to the left, right? So it's not the length, but it's the direction. It's going to be negative. But anyways, that's later. So now if we have C is equal to 6, I'm just going to replace this with 6. Now let's go and simplify. Now before I even write my trigonometric ratios, I also see that I have the square root of 27. And in this form, a lot of times I'm going to ask you guys to simplify your radicals, all right, and simplify your results. So the square root of 27 can be rewritten as square root of 9 times 3, which is 3 radical 3. That's going to be very helpful in us completing our ratios in simplified form. So now if I do the sine of theta, which is going to be 3 over 6, which, guys, we can just rewrite as 1/2, right? That's a 6. The cosine of theta is going to be 3 radical 3 over the hypotenuse, which again can be rewritten as square root of 3 over 2. The tangent of theta is going to be the opposite over the adjacent. So a lot of times we'll write this as 3 over 3 square root of 3. Now obviously the 3's divide out. So we're left with 1 over the square root of 3. A lot of times I will ask for a simplified answer to have the denominator rationalized. So therefore the radical rationalized. So to do that, all you're going to do is multiply by the square root of 3 on the top and the bottom. And what you have is the square root of 3. Square root of 3 times square root of 3 is going to be the square root of 9, which is just 3. So this answer simplifies to, oops, watch it. OK, now moving on to the reciprocal editing. I like to do these first. What? So this reduces to 1 over the square root of 3. I multiply by the square root of 3 on the top and the bottom. 1 times the square root of 3 is the square root of 3. Square root of 3 times the square root of 3 is the square root of 9, which is just 3. Okay? So now when we're doing the reciprocal identities, we could go back to this and say the reciprocal identities is hypotenuse over opposite, it's hypotenuse over adjacent, or it's adjacent over opposite, and then simplify it. But we also want to kind of like utilize our time a little bit faster, guys. If the cosecant of theta is just the reciprocal of this, well, then let's just rewrite it as a reciprocal, 2 over 1, which is just 2. Here, you can just rewrite this as your reciprocal, which is 2 over square root of 3. Now, again, we have to rationalize the denominator here. We don't want to divide by a radical. So if I rationalize the denominator here, I now end up with 2 square root of 3 over 3. And then over here, I could rationalize the denominator here. I'm sorry, I could take the reciprocal of this, but I don't really want to take the reciprocal of square root because I'm going to have a radical in the denominator. Couldn't I also just take the reciprocal of this, right, of that simplified form, which is square root of 3 over 1, which is just the square root of 3? Yes?
I didn't do it like that. I just did the hypotenuse over, like, for
And you can do that fine.
yeah, but I didn't get the same answer.
Which one?
For secant.
For secant, you took the what? You took the hypotenuse, which is 6, over adjacent, which is 3 square root of 3.
Yes. And then I got 2 over radical.
Right. And then did you rationalize the denominator? So if you rationalize the denominator, you'll get my same answer. Okay? Anybody have any questions, at least on the basic 6 trigonometric functions? All right, there you go. That is it for that. Well, that was all, tell you the truth, that was all geometry. I mean, there wasn't anything I introduced